Earth has always gone through climate changes. Ice ages covered entire continents in frozen sheets. Warmer periods turned deserts into lush forests. But what causes these shifts? For a long time, nobody had a clear answer to this question. In the 1920s, a Serbian engineer proposed something different. The answer wasn't on Earth's surface at all. It was in the way our planet moves around the sun. This idea would change how we understand climate forever. The theory is called the Milankovitch cycles. These are slow changes in Earth's orbit and the tilt of its axis. Over tens of thousands of years, they change how much sunlight reaches different parts of our planet. And sunlight drives our climate. Three main factors control this cosmic dance: the shape of Earth's orbit around the sun, the angle of Earth's tilt, and a slow wobble in Earth's rotation. Each one affects climate in a different way. Together, these three factors create patterns that match real evidence. Ice cores from Greenland show cycles of warming and cooling. Ocean sediments reveal the same thing. The data lines up with what the theory predicted. But here's where it gets interesting. Scientists found something in the data that nobody expected, something that would challenge everything we thought we knew about how these cycles actually work. Let's start with eccentricity. Earth's orbit isn't a perfect circle. It's an ellipse that stretches and shrinks over about 100,000 years. When the orbit is more stretched, the difference between Earth's closest and farthest distance from the sun grows larger. This matters because it changes how much solar energy we get throughout the year. A more stretched orbit means bigger differences between seasons. A more circular orbit spreads the sunlight more evenly across the whole year. The second factor is obliquity. That's the angle of Earth's tilt. Right now, it's about 23.4 degrees. But it shifts between 22.1 and 24.5 degrees over roughly 41,000 years. When the tilt is greater, summers get hotter and winters get colder. The seasons become more extreme. When the tilt is smaller, everything becomes milder. This has a huge impact on polar ice. The third factor might be the strangest. It's called precession. Think of a spinning top that slowly wobbles as it spins. Earth does the exact same thing over a cycle of about 26,000 years. This wobble changes the timing of seasons. Right now, the northern hemisphere has summer when Earth is farthest from the sun. But thousands of years from now, summer will happen when we're closest to the sun. That subtle shift could be enough to start or end an ice age. It all depends on how precession combines with the other two cycles. The interaction between them creates the pattern. So do these cycles actually cause ice ages? The evidence says yes. Climate records show a strong match between orbital cycles and glaciation periods over the last few million years. The correlation is hard to ignore. During ice ages, huge ice sheets covered North America, Europe, and parts of Asia. These expansions lined up with specific orbital combinations: low eccentricity, smaller tilt, and winter happening at the farthest point from the sun. Ice core studies from Antarctica and Greenland confirm this. Scientists compared sunlight changes over time with actual temperature records. The match was surprisingly close to what the calculations predicted. But the theory faced a serious problem, one that scientists still struggle to explain, and it happened about 1 million years ago when everything suddenly changed. Before 1 million years ago, ice ages happened every 41,000 years. That matched the obliquity cycle perfectly. But then something shifted. Ice ages started happening every 100,000 years instead. That matches the eccentricity cycle. Here's the problem. Eccentricity has the weakest effect on sunlight of all three factors. So why did climate start responding to the weakest cycle? One idea is that larger ice sheets made the system more sensitive. Another possibility involves carbon dioxide. As ice sheets grew, atmospheric gases may have started playing a bigger role. The climate system became more complex with many feedback loops working together. There's another puzzle called the Stage 5e paradox. About 130,000 years ago, orbital models said it should have been colder, but geological data shows the opposite. It was one of the warmest periods in 500,000 years. These mysteries led scientists to look beyond Earth. If orbital cycles affect climate here, they should work on other planets too. And Mars turned out to be the perfect test case. Mars has a much wilder axial tilt than Earth. While our tilt shifts between 22 and 24 degrees, Mars can swing from 10 degrees all the way to 60 degrees. This creates extreme climate swings. During high tilt periods, Mars's poles get more sunlight. Ice caps can melt and water moves toward lower latitudes. This might explain why Mars shows signs of ancient rivers. Water may have flowed during certain orbital phases. Missions like Mars Odyssey found layered deposits at the poles. These layers show cyclic patterns that match orbital cycles. The same theory that explains Earth's ice ages works on Mars too. Even the gas giants show these effects. Saturn's orbital changes may affect its ring system. Particles in the rings behave differently depending on orbital variations. Material gets lost or transferred to the planet over time. Neptune experiences something similar. Changes in its wobble may affect storm frequency. Hubble observations show periods of increased storm activity that could be linked to orbital cycles. The pattern appears across the solar system. These discoveries show that orbital cycles aren't just an Earth thing. They're a natural result of how gravity works. Wherever a planet orbits a star, there are orbital variations, and those variations change climate. So, do these cycles explain today's warming? Not directly. Orbital changes happen over tens of thousands of years. Recent warming happened in just decades. That points to more immediate causes like human activity and greenhouse gases. But understanding these cycles helps us see the bigger picture. Climate has always changed and will keep changing for natural reasons. The Milankovitch cycles remind us that Earth's climate is part of a cosmic dance involving the entire solar system.